Hello everyone. This is section 14.7, normal lines and tangent planes. We'll see if we can get through it in one part. If not, we'll have two. First definition is for a normal line to a function given by z equaling a function of x and f of xy at a particular point. So x sub 0, y sub 0, z sub 0. So these vectors, normal vector is given by, we use n sub I for the inward normal vector, and it's just the partial of f with respect to x evaluated at the point x sub 0, y sub 0 times I, plus the partial of y evaluated at that same point times j, and then minus k. And so that we call the inward vector, and then we have, there should be n sub O for the outward vector. And it's just, notice it's just the opposite. So here's an example. Find a vector normal to this vector, or to this function at this given point. So we're going to use our definition. It doesn't matter which one you use. We'll stick with the inward. And basically, we'll say that we'll replace z by f of xy. And then we'll calculate the two partials. The partial with respect to x is 2x. The partial with respect to y is negative 2y. And then into our formula. Okay, so this would be the normal vector. I guess we actually should have vector notation above each of these as well. Sorry about that. Let's say in general of xy could be given by f sub x, 2x times I, and then plus f sub y, which would be minus 2y times j, and then the minus k. So that would be the inward. And then you could plug in the point, so then we'd have that n sub I evaluated at, it's really just the point 2, 2, because it's not an implicit function, it's an explicit function. Z is given explicitly in terms of x and y. So then we just plug in the x is 2, and the y is 2. Oops, and then we carry along the negative k, of course. So it looks like 4i minus 4j minus k. Okay, so that's all there is to that. But I'm going to suggest the following definition to be used from now on. It's for implicit functions. And because it's for implicit functions, it's going to work for all situations. So we say that a vector normal to an implicit function of x, y, and z at a particular point is given by, it's pretty much the same thing, partial of f with respect to x times I, with respect to y times j, but then with respect to z times k. So here's an example. What we do is we first form the function, the implicit function, f of x, y, z. And so we're going to transpose our z to the right-hand side. So we'll have x squared plus y squared minus 1 minus z. And then, just like we did in the last example, now we're going to need three partials. So let me just do it off to the side here. Actually, let me do it right below. F sub x, I won't use the functional notation, is 2x. F sub y is 2y. And f sub z is negative 1. So then the normal vector in general at any point x, y, z is given by 2xi plus 2yj minus 1k. And then if we want the normal vector at the point 1, 2, 4, it's just simply 2 times x is 1 times I plus 2 times y is 2 times j, and then just minus your 1k. And so that gives us 2i plus 4j minus k. And I just wanted to point out here that, and again, this is going to be the best definition to use, or implicit form. But notice that the original form for the explicit form, that works the same because you've got, so this is for the explicit. The formula was that the normal vector at the point, if you want to say the n-word, xy would be f sub xi plus f sub yj, and it's just, it always says minus k, notice, so that when you plug in the partials, we get the exact same thing. Because if the function is explicit, that is z equaling whatever, so z equaling whatever we have here, when we transpose that z, it becomes negative z, and its partial is always negative 1, therefore that's why we always have the negative k. And then of course, you can evaluate this at the point, it would just be 1, 2, because it's a function of x and y. So 2 times 1 is 2i, plus 2 times 2 is 4j, and then minus the k. So of course, oops, and let me put a little hat on that one there. So of course we get the same thing. But it is best to use this implicit version because it works for everything. So here's an example where the function is given implicitly. So we'll form the implicit function f of x, y, z. So probably easiest just to bring the 9 over to the left. So x squared plus y squared plus z squared minus 9. So you have to set it to 0, basically, and call it f of x, y, z. And then you can calculate the partials. And I'll do them off to the side here. Partial with respect to x is 2x. Partial with respect to y, 2y. And partial with respect to z is 2z. So as a general function, a general vector that is, n of x, y, z is just 2xi plus 2yj and plus 2z times k. Now, you know, a function that's this basic, you really don't need to show these partials off to the side if you don't want to. I mean, you could jump right to, you know, substituting them into our formula for the normal vector. Okay, but now our point is 3, 0, 0. So 2 times x is 3i. Kind of silly to show this, but 2 times y is 0. K, and similarly, 2 times 0 is z times k, so we just get 6i for our normal vector. Okay, so now we consider, so now we know how to find normal vectors to a surface. Now we consider finding the tangent line, or excuse me, the normal line and the normal, and a plane that's tangent to the surface. So recall from previous units, the equation of a plane that contains this point is given by a times x minus x0, b times y plus b times y minus y0 plus c times z minus z0 is equal to 0. And that's where ABC is the normal vector. So if we know a couple things to note then, for a plane that's tangent to a surface, the normal vector is the normal vector, that formula that we just found. So that's going to be pretty straightforward. And that's actually the gradient. So the gradient gives us the normal vector that's tangent, that's normal to a tangent plane. And remember, the notation for the gradient del of the function at a point is equal to the normal vector at the point, is basically what we're saying there. Okay, so to summarize this as a theorem, it's saying if the gradient's not 0, then the gradient at a point is the normal vector to the function at that point, and therefore the tangent plane is going to be, see, these are the f sub x evaluated at the point, and the f sub y, and the f sub z. Those are really the a's, b's, and c's, which is the normal vector. And then similarly we have for the normal line, the parametric equations that we studied in the first unit. So this would be essentially x equals x sub 0 plus at, y equals y sub 0 plus bt, and z equals z sub 0 plus ct. So we don't have to really, be too formal with the functional notation and all, the x sub 0, y sub 0, z sub 0 thing. So let's look at an example. Okay, so let's see if I can focus that a little bit better. That's good. Okay, so here we want to find the equation of a tangent plane and the parametric equations for the normal line to the surface at a given point. So we're going to do two examples. Once again, we're going to suggest, no matter what, using the implicit version. So f of x, y, z is going to be, okay, here probably easiest to take the z and move it to the right. So x squared over 4 plus y squared over 4 minus z. We'll find the three partials. F sub x would be, okay, we get 2x over 4, or x over 2, or 1/2 x, however you want to write it. F sub y would be 2 over 4, 2y over 4, or y over 2, and then f sub z, as we expect, it's -1. Okay, so then the normal vector at any point, x, y, z, is going to be x over 2I plus y over 2j, and then minus k. So now the normal vector at the point 2, 2, 2 is going to be 2 over 2, or just 1I, plus 2 over 2, or 1j, minus k. So then that tells us that the normal vector in the form, let's say, of ABC So this is a vector that's normal to the tangent plane. That's just going to be 1, 1, and -1. So now we can find the plane, or the equation of the plane, that is, because here's our point, x sub 0, y sub 0, z sub 0. So I'm going to write it like this: a times x minus x sub 0 plus b times y minus y sub 0 plus c times z minus z sub 0 is 0. So that's the easiest way to look at it, rather than using, the f sub x, f sub y, and f sub z. If we just get that normal vector, call it ABC, then we'll be able to plug them in easily, looking at this form for the equation of the plane. So 1 times x minus 2 plus 1 times y minus 2, and then minus 1 times z minus 2 must be 0. And we'll do some algebra. X minus 2 plus y minus 2 minus z plus 2 is 0. So our general form, x plus y minus z equals, let's see, that's -4 plus 2 is -2, transpose to the right, and we get plus 2. So that's our tangent plane. Just stick the word tangent in there. Okay, and then the tangent line is given by, again, I'm going to say x equals x sub 0 plus at, y is y sub 0 plus bt, and z is z sub 0 plus ct. And then we'll make our substitutions. And so we have, again, the point up here at 2, 2, 2. And then we use the respective a, b's, and c's. So x equals 2 plus 1t, or just 2 plus t. Y is 2 plus 1t, or 2 plus t as well. And z is 2 minus 1t, or 2 minus t. Okay, so we're about at the 18-minute mark. I think I'll stop there. Got a couple more things to do, but probably shouldn't take more than about 15 minutes. So we'll come back and we'll do part 2 of section 14.7 when you're ready.